When everything is written to an immutable shared ledger, where do you hide sensitive data and how do you honor deletion laws? In this module, we'll unpack that tension. How to model data for integrity while still meeting strict privacy and confidentiality requirements. Blockchains are often called shared truth machines. That's powerful. But in enterprises and governments, not every truth can be shared. You need transparency, auditability, and immutability. Yet you must also protect trade secrets and comply with privacy laws like GDPR. This is the core paradox of shared ledgers. Ignore it, and designs fail or get blocked by regulators. Architect for it, and ledgers can actually become compliance enablers. A key mindset shift for architects is this. A blockchain is not a general-purpose data store. If you put full documents, PII, or raw business payloads on chain, you're effectively publishing them forever. Keys can be rotated, algorithms can break, policies can change, but that ledger copy is permanent and replicated. So treat any on-chain content as if it's globally visible. Use the ledger to store proofs and references, not the sensitive data itself. That leads to the golden rule for modeling data on blockchains. Put proofs on-chain, keep rich data off-chain. On-chain, store minimal, high-value facts, hashes, state transitions, evidence that something happened at a specific time. Off-chain, keep personal data, secrets, large documents, and media. The ledger should answer, can I verify this claim? Not, what is the full record? In short, don't store the data, store the proof. Hybrid trust architectures often use a simple but powerful pattern. Only the fingerprint of a document goes to the blockchain, while the full data stays in a traditional database. You run the document through a hash function like SHA-256, store that hash on-chain, and keep the document off-chain. If anyone changes even 1 byte off-chain, the hash no longer matches, so integrity checks fail immediately. Combine this with digital signatures and you know who committed which fingerprint and when. You get tamper-evidence and traceability without exposing sensitive content. When you think about off-chain storage, imagine the ledger as the control plane and these other systems as the data plane. Traditional SQL or NoSQL databases give you fine-grained access control, complex queries, and the ability to delete or correct data under regulatory pressure. Content-addressable systems like IPFS offer resilient, distributed storage with strong integrity guarantees, but weaker governance. Enterprise document management systems add records management, retention policies, and rich audit trails. In real solutions, you typically anchor hashes on-chain and combine these options to balance integrity, privacy, and compliance. Now let's ground this with a quick example. Imagine a supply chain network where all parties share one ledger, but pricing is commercially sensitive. Supplier A and manufacturer B can place their pricing agreements into a private channel. Only their nodes hold the transaction data, and even the fact that the transaction exists. Competitor C just sees that the overall network is healthy. The benefit is strong business confidentiality. The trade-off is reduced global transparency, which can complicate network-wide analytics, audits, and dispute resolution. Securing shared ledgers is not just about encrypting payloads. Payload encryption protects the actual business data, but metadata usually remains visible. Who talked to whom, when, and how often. That metadata can leak sensitive business intelligence. So practice minimization, aggressively reduce what metadata you emit and retain. And remember, encrypted traffic can be recorded today and decrypted later if keys are compromised or cryptography weakens. Zero-knowledge proofs sound exotic, but the idea is straightforward. You can convince someone a statement is true without exposing the underlying data. They learn the outcome, not the details. For example, a bank can prove it's solvent, or a citizen can prove they're over 18 without revealing exact balances or birth dates. In regulated environments, this is powerful. You get strong, on-chain verification while leaking the minimum possible information. You can think of privacy techniques as a spectrum you slide along depending on regulation and business needs. At the high transparency end, you keep data off-chain and anchor only hashed references. Everyone sees the same evidence, but not the underlying records. In the middle, private channels and pseudonymization restrict who sees what, while masking real identities behind stable, auditable IDs. Tokenization replaces sensitive values with tokens, and indirection points to tightly governed systems. At the high privacy end, Zero-knowledge proofs let parties verify rules without revealing the underlying data at all. This brings us to one of the most famous tensions in regulated blockchain design. GDPR says individuals can demand that their personal data be erased. Blockchains, by design, keep an append-only, permanent history. Those two ideas clash if you try to literally delete past blocks or transactions. The modern approach is different. You keep the ledger intact, but design for functional erasure by making data inaccessible or unintelligible in practice. Encrypt and forget is a practical way to reconcile immutable ledgers with deletion requirements. You keep only encrypted data and treat secure destruction of the decryption keys as deletion. Once those keys are gone, the ciphertext is mathematically unreadable, even though it still exists. Regulators in many jurisdictions accept this as functional erasure, but only if your key management is rock solid. That means provable key lifecycles, controlled access to HSMs or key vaults, tamper-evident logs of key creation and destruction, and clear policies tying data retention rules directly to key retention periods. Data residency is another non-negotiable in regulated environments. The rule is simple. Regulated data must remain inside its legal jurisdiction. With blockchain, the common pattern is to geofence nodes. You run full nodes with full data only inside the allowed region, and let cross-border nodes see just hashes or derived non-personal data. That still gives you global integrity and auditability without exporting raw records. But remember, where nodes are physically hosted is ultimately a legal and policy decision, not just an architectural one. As you move toward implementation, you can use this as a quick decision flow. First, classify each data element. Is it public reference data, business confidential, or explicitly regulated personal or sector data? That classification drives everything else. Next, decide what actually goes on chain. In most regulated environments, you anchor hashes or minimal metadata and keep full records off-chain under existing controls. Then, pick your confidentiality mechanism. Simple private channels might be enough, but for cross-domain proofs, evaluate ZKPs. Finally, design lifecycle and deletion strategies up front, so right-to-be-forgotten requests are technically and legally actionable. The core idea is trust without giving up control. You design hybrid architectures where sensitive data stays in existing systems and the ledger anchors proofs, policies, and shared state. Done well, this gives regulators and auditors strong evidence while preserving confidentiality and performance. Carry this forward. Blockchain is your distributed trust anchor, not your data lake and not your only system of record.